Hello and welcome to lecture number 5 for photo and non-photorealistic rendering. I'm your instructor as always, Leslie Eisted, and in today's lecture we are going to cover the wonderful topic of global illumination, which is going to give our images that real photoreal lighting. Because what we've got so far, not so much. But before we get into that, just a couple things we should make note of. First, assignment 2, if you haven't taken a look at it yet, I would recommend that you take a look at it as soon as possible because you are going to be asked to render several scenes with very specific properties. And some of those scenes can take a little bit of time to actually do. I think when I was doing the first one, it might have taken about 10 or 12 hours to render that one alone. So do get started now. And if you need any resources for doing that rendering, please let me know as soon as possible so we can make sure you have access to render machines in the lab, remotely, of course. The other thing I want to just remind you of it is if you need any assistance, don't forget to send me an email or come on Discord and we can have a chat. And there are also some resources posted on Brightspace. And when you're working on assignment 2 and future assignments, if you would like to use any other assets than the ones that have been provided, and I highly recommend it, because the goal here is to create interesting scenes, right, that are photoreal at the moment. So feel free to go onto websites like TurboSquid and so on and grab some of the assets from there. Just indicate where you've got them from. I don't expect that you're going to pay for assets. There's lots of free ones available. If you want to pay, that's up to you, but you don't have to do that. All right. So where we left off last class was talking about reflection and refraction and subsurface scattering and some of the different lighting models that we can implement in a ray tracer to give us some of the different optical properties that we would see in the real world. So, you know, any time you have something that's reflective, I don't have any reflective objects right here right now, you would actually see something in it. And then anytime you have a transparent object, you see through that object, but not perfectly, and it might be distorted. So we looked at all of those different properties. And you might be thinking, well, when you have reflection and you have refraction and you have shadows, and we have soft shadows from area lights and volumetric lighting, and we've got environment mapping, that's all the kinds of things that we need, right? Isn't that all that exists in the world? Well, let's take a look. So can we use what we have seen so far to simulate all of the possible phenomena that would be observed in the real world? Okay, well, let's do an experiment. Let's see, and we're going to do the experiment in Houdini. But before we do the experiment, let's think about some of the different optical effects that we might be trying to do. So this is a photo of a glass of water. This is actually from Wikipedia, and there's a light shining into the glass, and you can see it looks like the light is in the glass, which is interesting, because this is actually looks like it's an outside object. And then on the surface, where the glass is resting, there's this bright, focused light. We call these caustic effects. And you don't need a glass of water. You can take a white mug and look inside, and you'll see here how the rays of light have been focused into being a source of emission where there is none. And everything we've done so far, actually, reflections, refraction, subsurface scattering, can we do this? No, actually, we can't do this. And if this is not a caustic isn't something that you've ever seen before, I highly recommend you get a glass and a light and just move the light around the glass and you will see these effects. We can't do that right now with the ray tracer that we have created so far. And if you're sitting there wondering, well, it's not that common, it is actually pretty common. So there's all kinds of different lighting interactions like that. So for example, it's not just, lights shining through glasses. There's also things like prisms. If we shine a light through a triangular prism, we know that the white light goes in and we get a rainbow. It's the white light separates into a rainbow effect. And the ray tracer that we've built so far cannot handle that either. And if you wanted to do a magnifying glass, if you take a magnifying glass outside onto the sidewalk, you're supposed to be able to, start fires and stuff with it. Yeah, we can't simulate that either with what we've built. So maybe we should take a step back and try to something much, much simpler to see, can we do that? So the simple thing that I want to show you, our experiment for the day, is we have a floor, we have a mirror that's angled downwards 45 degrees, and I'm going to shine a spotlight at the mirror, and it should reflect towards the ground plane. And so the light that is reflected by this mirror should get reflected and end up lighting the ground plane. That is what we expect. That is what we want to happen, because we know if we had a flashlight and we had a mirror, that is exactly what would happen. So the question is that what's going to happen? So I know this is a very strange looking image, but what you've got here actually is, it's hard to see because of the reflections. There's actually a mirrored surface. It's a perfect mirror, and it's at 45 degrees facing down. There's a white and a blue walls in behind and a red floor, and all of the walls are diffuse surfaces, so they're not reflection. And what you can't see here is that there's actually a spotlight shining onto this mirror right about here. And you can't see that it's there because it's not actually a physical object. It's just some math. But the other reason why we cannot see the spotlight in this particular image is because it's not lighting the mirror, and there's no light being reflected from the mirror onto the ground. So this was a really simple experiment. It's something that we know should be true, but that's not what we are seeing. So the ray tracing that we have done so far can't even reflect light onto other surfaces. And there's a name for this. It's called indirect lighting. This point on the ground is not being directly lit by the spotlight, because the spotlight would be pointing here. This point on the ground should be indirectly lit by the spotlight by virtue of the fact that it's bouncing off of the mirror and then lighting that point. This is what we should actually observe. So I turned on some magical effects inside of Houdini so that you would see this result here. So this is the traditional ray tracing that we've seen so far, and this is me turning on a form of indirect lighting. We can now see that the spotlight has hit the mirror and has reflected and indirectly lit this patch on the ground, and now we can of course see that in the mirror. This is a more realistic version, but we don't have the tools to do that yet. So ray tracing and everything we've seen about ray tracing so far handles what we know as direct lighting. It's literally, I'm trying to grab this light on my desk here, which is a little dusty. This is my light. When you have direct lighting, you have a light source like this LED spotlight, and it is directly illuminating the object. I know this light isn't on. It would blow the camera out if it was. So this light would directly light this pen. That's direct lighting. And that's all we've actually done with our ray tracer so far, is direct lighting. We haven't actually considered the situation where you have indirect lighting, where the light is bouncing off a surface and then illuminating something else. And what's interesting is it doesn't have to be a single bounce. It can actually be several bounces, because you might have a whole pile of mirrors, or the light may reflect off the mirror down onto the diffuse surface, and diffuse surfaces actually do reflect light, just in all directions. So that would cause light to reflect elsewhere and indirectly light other parts of the scene. And that indirect lighting is not handled by what we've done so far. Now, this lecture is entitled, Global Illumination. Now, the truth is global illumination actually includes both the direct and the indirect lighting. But a lot of people, when they're referring to global illumination, are actually referring just to the indirect component. So what global illumination really is it's just describing all of the different kinds of light interactions that you would have in a scene. So things that are being lit directly, it's describing the indirect lighting, and so on and so forth. And there's lots of different ways and things that contribute to indirect illumination as part of global illumination. And one of the big ones that we often forget, we're going to deal with the mirror example later. Let's deal with something a little simpler first, and that's diffuse reflectance. So if you have a diffuse object, looking for a diffuse object. So I have this book, and the cover's shiny. This is not a diffuse reflective surface. It's a shiny surface, which means that light is being reflected in a particular subset of directions more often and in a higher amount than in other directions. But if I open this book up to one of the random pages, you can see that there's no shiny component. The pages of this book are what we would call diffuse or Lambertian materials. That means that when light hits it, it's going to be reflected in all directions equally. And you might be like, well, why does this matter? What is diffuse reflectance? Well, what's really interesting about diffuse reflectance is that you get this color bleed. And I actually have a red object hiding on my desk. I can grab it. Probably should have grabbed this beforehand so I wouldn't knock everything off my desk. So we have the book, and we open the book, and we put the red object in front of the book. And what you can kind of see here, even though this is a shiny object, this would work even if this object was not shiny. You can see that the shadows and a bit of the red color bleeds onto the diffuse box. And again, this works even if this cup was a diffuse object. It's not a diffuse object. So this is an interesting property where you have diffuse objects. They are still reflecting light, but we're not accounting for that. So what happens is you have this incident white light. It hits a diffuse red surface, and red light gets reflected in all directions. And now if you have white walls in this room, those white walls are seeing some red light, and that's going to impact their appearance in the rendered image. So let me show you the difference between having that indirect lighting from a diffuse surface and not, or having it and not having it. So here I've created a very simple image. This is what we call a Cornell box. It's a famous model or scene setup that we use to test different kinds of reflection and global illumination. It's just a box. We usually put an area light at the top of the box, and that's going to give us some nice shadows, but also because certain kinds of global illumination algorithms that we'll be looking at today do not work for point light sources. They only work for area lights and volumetric lights. So Cornell box, area light at the top. We usually put a sphere in the middle because why not? And then I have all of the surfaces in this Cornell box being diffuse. So there's no shiny things in this scene. So we've got a white ball, a white wall, a white ceiling, a white floor, and then a red wall and a blue wall. you'll see that the shadows here are gray, and the white walls, due to the poor lighting conditions, are also gray. And there's no color bleed from the red wall onto the back wall. And it looks fine, right? If you didn't know that there was something wrong with this image, you probably, in advance, you probably wouldn't say anything about it. But look at this. This is the exact same scene, but what I turned on was diffuse reflectance, so indirect lighting from diffuse surfaces. What you immediately see is that the image is brighter. And it's brighter because the light from this area light is going to hit the surface, and it is going to bounce off and light other surfaces. So the image to start with is a bit brighter. And if we look at this, it makes a lot more sense. We still have darkness in these deep corners of the room, but now the rest of the scene is a bit better lit, the way we would anticipate. Furthermore, we are seeing some of the colors of the walls bleed onto other surfaces, because we know that this red wall, we are observing red because it is reflecting red light. So the light that is reflected by this wall is red, and it is coloring the sphere and some of the floor and the back wall red, ceiling as well. So that's pretty cool, right? So without, with. And now you realize that this image is much more photoreal than this one here. This one here looks like a bunch of boring plastic balls in a plastic box. This one here has a certain warm tone that the other one did not. So that's one kind of indirect illumination we're going to look at today. Another kind of indirect illumination we're going to look at is the caustics that we showed you at the very beginning. What caustics is where you have a surface, and it doesn't have to be a transparent surface. It can actually be a piece of metal, something that is just shiny. You have a surface that has a particular shape, and it's actually causing the light rays to focus and be reflected onto something else. And it creates bright spots and bright patterns. And you typically see this with metal, glass, water. So the waves actually bend the light as they go in, and they can actually cause the light to focus and create bright patterns on the bottom of the seafloor, which is pretty cool. And we call this caustics. So to give you an example, this is a glass that we have rendered, and this has none of that indirect illumination algorithms turned on. So there's no caustics being applied here. This is how we would have ray traced it from our previous lecture. If I now turn caustics on, that is, I'm going to simulate the lights as they travel through this glass, this is the result we get. And instantly we see where before we might have thought this looks pretty realistic, we realize, oh wait, it wasn't. One of the key giveaways here is actually the shadows. If you have a transparent object, it doesn't cast a solid shadow because the transparent object transmits light, which means that the shadow shouldn't be as strong. The shadow is really strong here. It's as if this glass was perfectly opaque, and yet it's not. So when we turn on indirect lighting, not only do we get the caustic effects where the light rays are being focused, but we also end up with shadows that are not solid. They reflect the fact that we are the shadow of a transparent object. So there you go. Without caustic effects and with. Clearly we are moving in a direction of greater realism. So these are lovely effects. Absolutely lovely effects. This is what we would like to see in our photoreal images. But how do you do it? And I mean, to be honest, it's fairly easy to turn on and off in tools like Houdini and Maya and whatever rendering tool you are using. Oh, excuse me. But how is that actually implemented? And as it turns out, there are a lot of different algorithms that are used to simulate indirect lighting as a part of global illumination. And we're going to look at a few, but not all of them. So some of the different ones you might have heard of is Radiosity, and we're going to go into greater detail on some of these, by the way. There's also one called Photon Mapping. Lovely spelling mistake there. There's also one called Path Tracing. And on the note of path tracing, if you've heard of path tracing, you might have also heard of bidirectional path tracing. There's also the metropolitan light transport. There's ambient inclusion. There's all different kinds of algorithms that we use to simulate either subsets of indirect lighting or indirect lighting in general. So just to give you a greater sense of how this is going to improve the photoreal quality of our scene, I have this image here, and it's got a bunch of glass and metallic objects. Ooh. And it looks pretty good, actually. You know, you got shiny gold, nice glass. But the real giveaway that we have a bit of a problem with this scene is the fact that the shadows of the transparent objects are solid. That's not what shadows of a glass would look like. So when I turn on the global illumination, that's what I get. And again, you're going to instantly see that the scene is significantly brighter. You're going to see a lot more internal reflections and refractions. But we also see the caustic effects on the walls. We see non-solid shadows. And I actually see the light being reflected from the horse and the apple statue and actually providing some indirect illumination to the wall and the area around it. And this is what we expect. So now we're going to take a look at the algorithms we use to turn this interesting but not really photoreal image into this one, which looks a lot more realistic. And we are going to start with the one that I learned first, which is called Radiosity. And Radiosity is actually only going to consider a subset of the possible indirect illuminations. The observation that we're making is that diffuse surfaces actually reflect light and therefore provide some indirect lighting to other surfaces in the room. And essentially what we're saying is some of the radiance that is received at a surface is radiated outward as a reflection, hence radiosity. And radiosity is actually based on the heat transfer equation. Now this method is actually extremely limited. It can only be used to simulate indirect lighting of diffuse surfaces. So shiny objects like this vase that I actually use for pens now, yeah, can't do that. It also cannot do things like point light sources, mirrors, or transparent objects. So it's really limited to colored pieces of paper or things that are perfectly diffuse. At least that's what it excels at. I'm not going to tell you that there isn't some modification to the algorithm that is capable of doing something else. So there's actually, in the terms of radiosity, there is, even within this method, many different algorithms we can use to solve this problem. One of the ways that we can do it is using something known as progressive refinement. So we're going to start out with a really coarse solution to the problem that is mimicking the light bouncing between all of these surfaces. And then we're going to progressively refine it. So we do another iteration, a little better detail, and a little better detail. And we keep refining and refining and refining until we're not making any noticeable changes. And at that point, we stop this refinement process and we have a solution that we're happy with. Regardless, however, of which method that we use to implement radiosity, there is something that all methods do. Ooh, apologies. And that is that they subdivide the surfaces into little patches. And then we want to know for each patch, what can you see? You might be like, what does that even mean? Well, allow me to actually show you what we mean. And I've borrowed some of these images from this website down here, which I highly recommend you actually go to and read. It has a really great explanation with a lot greater detail in pseudocode to tell you actually what's going on here. So we have subdivided each of our surfaces into a bunch of small patches. That should actually be fairly straightforward if you're doing a bunch of meshes because you've got a bunch of triangles or quadrilaterals already. Now, if you have a big solid planar surface, you're obviously going to want to subdivide that because how that big planar surface gets lit depends on the region in which we are looking at. So after you have done that, what you're really doing is trying to figure out what part of the scene can this patch here actually see. Now, why do you need to know that? Here's why you need to know what each individual patch can actually see. Because if you cannot see a region, then that region cannot contribute light to you directly or indirectly. So you can only receive light from those patches that you can see yourself. Now, that's not to say you can't indirectly be lit from things that are behind you, because surely light will bounce and bounce and bounce and bounce and bounce. But you can only actually receive those bounces from the patches that are actually visible to you. And what we do is we take the sum over all of the incident light for the patch, and that becomes how much light the patch is actually seeing as a part of the rendering equation. So if we subdivide the world into a bunch of patches as suggested like this, and then we start doing iterations. So we might do the first iteration. Now the first iteration is effectively the first bounce. And then when we do the second iteration, we're getting the first bounce and the second bounce. And then 3 iterations would be the first, second, and third bounce. So we are bouncing light. And the more iterations we do, the more bouncing of the light we are permitting. Now, to make sure that we are keeping track of how much light is incident at a given part of the scene, we are going to use Lambert's cosine law, which we saw in our previous lecture, as a means for computing the contribution to a given patch given the incident light. So it's kind of similar to computing the brightness of diffuse surfaces. So you take the color of the patch and you multiply it by the intensity of the incident light. And then there's also, a normal in there and a light vector. Now, when do we stop iterating? We're going to keep track of how much of a change was made to the image after each iteration. And so long as the amount of change happening is above a certain threshold, we will continue iterating. But once the amount of change reaches some small threshold, we will stop iterating because we know that adding more bounces of light doesn't really contribute to the scene's appearance. So we start with 1 bounce, and then you get like 5, 10, 20 bounces. And as you can see, as you add the bounces, the image does get brighter, but it also feels a lot more warm and real than what we had before without even any bounces. Now we can implement this. It's fairly actually easy to implement this. In fact, these results that you're seeing on this slide and some of them on the next slide are actually results from the Radiosity renderer that I wrote 15 years ago, something like that. So what do you notice about these results. See, we've got these patches. I see the blue light is reflecting onto the white, and the red light's reflecting onto the white. And in this case, I have a bunch of white walls and a white ceiling, and the bright red floors reflecting up. It kind of looks bad, actually. And it looks bad because we have all these patches. And we can increase the number of patches. We can totally do that. The problem with increasing the number of patches, of course, is that it's going to take a lot more time. Because for each patch, you have to see what can it see, which means you have to send out a bunch of rays to see what you can see. And you're going to have to do that for every single patch in the scene. So the more patches you have, the more expensive it's going to be, but the better quality results you'll get. Even though when we subdivide into more and more and more and more patches, it's still going to give you a bit of a patchy, blocky appearance. So realistically, what we have to do is after this step, we're going to have to apply some interpolation and some smoothing so that we can get the nice, smooth result that I showed you here. That's a really nice, smooth result. And I know there's a little bit of grain. It's because I didn't want the image to take 16 or 20 hours. Yes, this is really slow. So that's the idea behind Radiosity. We are actually going to, from each patch, we are going to figure out what all of the world can you see. And then we are going to use what you can see from the world to light that individual patch using Lambert's cosine law. Now, one of the interesting side effects of the radiosity algorithms is that you don't actually need to have an explicit light source. You can actually just set certain patches to be emitters. So you don't have physical lights that you set in the scene. You just set this patch and this patch, you emit light. But we also don't have the ability to do point lights. This algorithm doesn't work for reflections or refractions and so on and so forth. So that's our algorithm for radiosity. Now, because of the limitations for radiosity, we actually don't tend to use it in many rendering applications because it doesn't handle all of those things that we just talked about. So maybe we should talk about some of the other possible algorithms that we could use to solve the problems of indirect lighting. For example, there's an algorithm known as path tracing, and path tracing is massively popular. Maybe not used so much today, but it definitely still exists in some rendering applications as an option. And it works pretty well. So the idea is there's the rendering equation. And if you go back to lecture 3, I didn't want to repeat that big equation here again. But if you go back to lecture 3, there's the rendering equation. And you might notice it has an integral in it. And the integral is where we are taking the contributions from all of the light sources in the scene and adding them all up so that we can figure out the final color of this particular pixel. What path tracing is trying to do is actually solve the integral component of the rendering equation. Yes, sometimes we try to solve math things using graphics ideas. It's kind of neat, actually. So there's 3 properties that path tracing kind of adheres to. One is we make the assumption that every object in the scene is going to reflect light, which means that every object in the scene is going to contribute in some capacity to the indirect lighting of the scene. This is essentially true in reality. If you look at the world around you, can you think of any object that wouldn't reflect light? I think the only object that I know doesn't reflect light in any way is that fancy black paint. I'm trying to think of the name of it. It's this ultra black paint. Okay, so I guess they're calling it black 3.0. I'm not sure. The idea behind the super black paints is that, oh, Vanta black. I knew it started with a V. It's like Vanguard black? That doesn't make sense. So Vanta black, and there's other companies that have been working on these particular black colors, is a paint or a coating that actually is designed to absorb as much light as possible, which if you're absorbing as much light as possible, it means almost no light is reflected. And it's actually really crazy. It's almost like the object doesn't exist. It's really cool. And, you know, there's people out there who want to paint their cars in Vanta black so that, you know, you're driving at night and nobody can see you because you're not actually reflecting anything. I think, if memory serves me, Vanta black might only reflect something like 0.3 or 0.7% of the light that is shining onto it. The point I'm trying to make is that in the real world, aside from scientist-created coatings, almost every object is reflecting light. So I feel like we've got this. We could put a check mark by the first statement. The second property we kind of adhere to is that there's no such thing as a light. What we mean by that is that surfaces can reflect or emit light. We are not going to actually have a specific kind of object known as a light. We are just going to say, here is a patch or here's a region and it is emitting light or it is reflecting light. So that's what we're going to keep track of instead. The third property is that surfaces are reflecting light according to some function of the incoming light direction and viewer direction. What we're actually saying is that every surface has a BRDF, a bidirectional distribution function, under which it describes what is the probability that light is reflected on a given angle. So, for example, a Lambertian surface, perfectly equal in all directions, whereas a specular surface is going to only reflect a small amount of the light in a certain range of angles. So we are assuming then for path tracing, every object reflects light. There is the possibility that a patch is an emitter and that we know the reflectance probability for all of the materials in the scene. Given those three things, we can actually implement an algorithm that gives us the radiosity, i.e. the indirect illumination for diffuse surfaces. It's also going to give us caustics, and because of its implementation, we also are going to get soft shadows, which is why path tracing is actually quite a popular algorithm. But it's not perfect. So we've made this assumption that the rendering equation is going to give us, you know, this perfect model of illumination in the world, and actually it doesn't. The rendering equation does not give you intense caustics. It does not account for radiation from space. It doesn't account for subsurface scattering for some reason. It doesn't account for fluorescence or iridescence. And if you're sitting there when it was fluorescence, fluorescence is like glow-in-the-dark paint. It doesn't account for that. It doesn't account for phosphorescence. It doesn't account for iridescence, which is things that reflect different colors depending on the angle under which you are viewing them. There's some really cool iridescent objects out there, which we'll talk about a little bit later. So the rendering equation isn't perfect, and since we are trying to solve the integral in the rendering equation, which is not perfect, path tracing is therefore not perfect and cannot simulate these properties either. That doesn't mean it doesn't look good, though. So how do we implement path tracing then? So what we're going to do is, it looks almost like ray tracing actually. We're going to send rays from the camera through each pixel in the image. And instead of sending one, we're actually going to send a bundle of rays. So a whole bunch of rays are going to get sent from the camera through a pixel into the scene. When each of those rays intersects with a surface point, we are then going to choose a random direction to shoot another ray. And the direction under which we shoot that reflected ray and the probability that we do or do not reflect a ray at that point is going to depend on the material's BRDF, so that distribution function describing how light is reflected off that surface. So for example, for a diffuse surface, where the probability of it being reflected is equal in all directions, that would mean that the random ray could be literally any random ray. Whereas if we had a shiny object, then the angles that we might be able to reflect on are very small. So we've got a bundle of rays. For each ray where it intersects, we're going to choose a random direction to shoot another ray. We are then going to, from that point, compute the contribution from the original ray for its color, and we're going to recurse. So now we're going to pretend that the surface point of intersection is now the origin, the camera, and we shoot the new ray that we randomly computed in the previous step and figure out what it can see. Compute its contribution, and continue. And what we do to get the color of the pixel is, for that bundle of rays that went out into the world through that pixel, we are going to take the average of all of the colors observed by that bundle. And since each reflected ray is randomly reflected, they're each going to probably see something slightly different. And so you end up getting soft shadows, because after all, that's kind of what we're doing for soft shadows, is sending multiple rays. And we're sending multiple rays here and then averaging them. Now, there's one thing you might notice. I didn't talk about step C here, which was stop when a maximum depth has been reached. What does that mean? Here's the problem. If we have some rays and they are bouncing around in the scene, bounce, 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 bounce. Okay, when do they stop? Because if I don't physically stop them, they may not stop. Now, if they don't hit anything, then that ray would disappear. But there is the potential for rays to bounce back and forth between the left side of the frame and the right side of the frame, and then back and forth, back and forth, back and forth. And now we have an algorithm that never stops. So in order to make sure that this algorithm actually terminates, which is really important, we're going to set a maximum depth. So a maximum number of bounces that we will permit before we stop the process and compute the contribution from what we've seen so far. And in a lot of ways, this does make sense, because light gets attenuated. And we talked about that before. So you do want to actually limit this. So I want to now walk you through what's actually going on in the path tracing algorithm, so you can picture it. So what we have here is, and I know you can't see it, there's a camera. And this plane or object here is our image plane. And we've sent a ray from the camera through a pixel into the scene. And this ray is a part of a bundle of rays, which means there's more than one ray, that we have actually sent. It intersects the sphere at this point right here. So that's phase one. From that intersection point, we compute the contribution based on the color of this sphere and possibly any direct lighting. And then we are going to choose a random direction in which to send a ray, and we're going to send it out into the world. And that ray is going to intersect potentially another object. And so the process repeats. And we tried to compute a random direction for the new ray to go. Now our new ray here didn't hit anything, so it's terminated. And now the final color of this point right here is going to be the average of all of the contributions for each of the bundle of rays in the bundle that we have actually sent. So here is, so this path here is going to be the path that was taken from the first ray in the bundle. So then we send another ray for our bundle from the camera through the image plane into the scene. It intersects the object, and now it generates a new random direction in which to reflect the ray. And so now it sends that ray off, and that ray intersects something else. And then it sends another reflected ray off, and it hits something else. And this process continues and continues and continues until either we hit nothing or the maximum number of iterations has happened. And then we take the contributions from each of these rays and we compute their average, and that's going to give us our color. But because of the number of rays we are sending here, we are going to get soft shadows too. So this is a pretty cool algorithm. Now, I don't actually have a path tracer. So this is actually an example of a result you would get from a path tracer from Wikipedia. And you can see all of the effects that we talked about. First, we can see that there's diffuse reflectance happening. The indirect illumination from a diffuse surface, this diffuse red, blue, and green ball are actually casting or some of their red, blue, and green light onto the other surfaces in the scene. So, first thing worked. We can also see that there's caustics happening in the scene. So this glass ball here has a lovely caustic effect reflected onto the ground. So the second optical property, we've got that. We've also got, if we look very carefully, there's also reflections, caustics going on in the scene. It's a very capable algorithm. Doesn't handle everything, but it does a pretty good job. Now, path tracing is a member of a family of algorithms known as Monte Carlo algorithms. And you might have heard that term before in previous courses, or maybe you haven't. But a Monte Carlo algorithm, it's a really neat thing. It's a way of solving a math equation by doing repeated random sampling. So to give you an idea what I mean by that, I'm going to open up this program. I'm going to draw with my mouse because I don't know where my pen is. So let's say you wanted to compute the value of pi. Now we know that pi is like 3.1415962, something like that anyways. We know that. But how could we arrive at this answer? How could we estimate the value of pi? Well, as it turns out, you can actually estimate a value of pi using Monte Carlo algorithms. It's a very simple algorithm. You create a box. Here's my box. Or not. Apparently that's, oh, it's a selection. It doesn't let me draw. Oh, they're going to make me actually physically draw a box. That's not going to be good. Okay, we'll go back to this. I thought they were going to let me actually draw shapes. So here is our box, and let's pretend this is an actual square. And this box, the sides of this box are going from -1, -1 to 1, 1. And inside the box, I inscribe a circle. Okay, it's like trying to draw a perfect circle inside an imperfect box. It's kind of funny. All right, so there's my circle inscribed inside the box. And the radius of this circle is 1, of course. Okay, so how am I going to compute pi from this diagram that I just drew? This is where the Monte Carlo aspect comes in. We're going to take a bunch of darts, and we are going to pretend that this little drawing I have is a dartboard. And we are going to throw darts at the dartboard. So let's start throwing some darts. So there's a dart, it lands there because I threw it, so it missed the board entirely. And since I threw the next dart, it missed it entirely. I keep throwing darts. And what I do is I keep track of the number of darts that landed inside of the circle versus the total number of darts that I threw. And as it turns out, that ratio of darts that landed in the circle to darts that I threw will help you compute pi. It's an estimate for pi by throwing darts at this special dartboard. Now, obviously, if you throw 2 darts, it's not going to give you an estimate for pi because you threw 2 darts, probability speaking, they both landed in the circle. So the idea with a Monte Carlo algorithm is you're doing repeated random sampling. You get a more accurate estimation with more samples. So in order to get a very realistic estimation for the value of pi using this dartboard algorithm, you might have to send 1 million or 10 million darts. And it probably sounds like it's really slow. Well, so one of the interesting things is that each sample, each repetition, is generally independent for a lot of these algorithms, which means that it's very, very parallelizable, which means you can put it on the GPU, your graphics card, and make it run much faster. So you could do 1,000 or 1,600 or 2,000 of these darts could be thrown at the same time. So that's pretty cool. And what path tracing is a Monte Carlo algorithm. We are using repeated random sampling. We send a bundle of rays. Each ray is a repetition. So each ray in the bundle is a repetition. It's a random sample because for each of those rays, we're taking a different random path. And then we're aggregating the results of all of those repeated random samples to give an estimation to the solution of the integral. And yes, Monte Carlo methods, this repeated random sampling, are one of the techniques that we use to solve many integrals. That's a pretty good job, actually. And it's much, much easier than solving a crazy integral. You could write a piece of code to do it, and it might take an hour, but you get a pretty good answer. You didn't have to do 16 pages of impossible integral math. So it's pretty cool. It's computationally intensive. It is something you can improve the performance of a little bit, but it's still pretty expensive. For our example with computing and estimating the value for pi, that's actually pretty fast. But if you were actually doing path tracing itself is really slow. I mean, so is Radiosity. They're both really slow. But you get better lighting results. Now, Radiosity hasn't generally been used for a lot of many films and things, but path tracing has been. So actually, the idea for path tracing dates almost back to the origins of ray tracing, which I believe ray tracing originated in 1984, if memory serves me. And path tracing was 1986. Now, in 1986, it wasn't necessarily the world's fastest thing, not necessarily feasible. It wasn't until I think the early mid-90s where people started really taking it seriously. And then the first film to be rendered with a path tracer was a movie called Monster House, which was released in 2006. So it took 20 years for us to actually get the computational abilities to actually do any real projects with path tracing. It's expensive, really expensive. Same with the Radiosity. And actually, one of the irritating things about when you're trying to do indirect illumination or global illumination, and you're going to find this when you're doing your scenes with it, is you'll have a look that you want to achieve in your mind. And I really recommend you actually plan it out on a piece of paper first. And then you try to create it and you render it, and you won't know what it looks like for like 17 hours. And then after 17 hours, you look at it and you're like, oh, you know what? The intensity of the area light was just too high, and it's causing everything to be blown out. But it's going to take you 17 hours to realize that's the case. Plan this stuff out. So again, there are lots and lots and lots of different algorithms that we use for our global illumination and indirect lighting. Something that you see used a lot more often now is photon mapping. Photon mapping is actually has some really cool benefits over the previous two methods. Now, it's more general. It's going to handle, like path tracing is going to handle reflectance and caustics, but unlike path tracing, photon mapping can also do subsurface scattering. And the thing that really separates, there's a couple things that really separate photon mapping from path tracing. Photon mapping is view independent. What you're effectively doing is you have this two-phase algorithm, and in the first phase, you compute what's known as a photon map. We're keeping track of how much radiance from each light source is leaving the light and going to each region of the image, and then how much is bouncing around. That photon map is then used when we ray trace the scene to help illuminate surfaces. The photon map was not computed from the perspective of the camera. It's computed actually from the perspective of the lights, which means that for any still scene, it doesn't matter where the camera is, you only need to have the photon map computed once. So it's a small advantage if you're going to be doing like an animation or doing anything like that. So what actually happens with photon mapping? Now, one of the things you'll note from the previous method of path tracing is that we were still tracing rays in reverse, from the camera through the image plane and into the world, backwards. Photon mappings goes forwards to create the photon map. So what we're actually going to do is we are going to send photons from each light source in the scene. And each of those photons, which is effectively just a ray with some extra information, is going to carry a portion of the light. So a light emits so much radiance, so much power. And each of the photons is going to be carrying a portion of it. So if you have 100 photons, then each of those photons carries 1/100th the power of the light. When the photons intersect an object, we will store that intersection in the photon map, keeping track of how much of that is absorbed, how much of the photon's radiance gets absorbed, flux gets absorbed. We will also compute, where did this photon get shot from. And then we are going to reflect the photon based on the BRDF of the surface. So that's going to say, give us the probability of whether there is a reflection, and then if we do have a reflection, the BRDF is going to give us, the ability to actually reflect the ray according to the reflectance model of the particular surface. So to give you a visual example of what's actually going on here, because again, it's kind of the opposite of path tracing, we have a light source, and we're going to send out a whole pile of rays, photons, from our emitting light source. And each one is going to carry a portion of the power. So we have 5 photons here, so each one, let's say, will carry 1/5 the power of the sun. What we're going to do then is the ray hits the object, and the photon map is going to store this intersection point, and it's going to store the amount of power the incoming photon came with it, and then it's going to compute how much of the light is absorbed. It's going to compute the color contribution of the point, and then we're going to reflect it out into the world to another object, and that's going to continue and continue and continue, kind of like path tracing. Now, because it is a probability, there's actually a chance that photons don't get reflected, they just get absorbed. And the idea is that the reflected photons are not just carrying light from the originating light source, but they're also carrying some of the reflected light from the objects that it has touched on its way to touching you. We can stop this process of bouncing around, of course, if we hit nothing, because there's nothing in front of us. Otherwise, we need to put in a limiter, just like with path tracing, to say, hey, stop bouncing, because you're going to kill my computer. So after we have done that, then we do the second phase, which is actually ray tracing. So now we're going to ray trace forwards as normal, which is going from the camera to the image plate and into the world. We're going to do all specular reflections and direct illumination as we would have already done. But now we have contributions from indirect lighting that we are going to add in to help solve our model. So what we are going to do is to compute the indirect lighting, we look at our photon map and we say, where are the k nearest photon intersections? Because each of those intersections indicates how much flux, how much light was actually received at that point by that photon. And then we are going to compute the total contribution of all of those k nearest photons by summing the photon contributions and then multiplying it by the BRDF. So this is all of the incident light from all of the photons we have in the map around this point, and now we multiply that by the BRDF to say how much of it we are absorbing, how much we are reflecting, and what is the probability that light gets reflected in various directions. So similar to radiosity and path tracing, photon mapping, as you can imagine, is incredibly computationally intensive. The more accurate results you want, the more photons you're going to need to send. For the record, the images that are used in this slide deck were done with photon mapping, and I believe I used 10 million photons. Yeah, I'll show you in a minute. If you do not use enough photons, then your accuracy is going to be really poor. It's going to be really patchy, really grainy. If you use too many photons, you may not get the you'll get quality results, but you could have got the same quality results for less photons. So it's kind of about finding the right balance. I can't give you a magic number of photons to emit from a particular light source simply because it depends on this algorithm you're using, because there's many variations on the photon mapping algorithm. It's going to depend on so much of your scene. We're just not going to worry about Now, how do we store the photon maps? Because that's actually going to be an added cost. We have, the cost of actually sending all these photons, but now we also have a cost for looking up the k nearest photons. How we do that typically is using a KD tree, which can help reduce the search time. And you can do other trees as well, but KD tree, there is an advantage that the height of the KD tree is O of log n, which means that a lot of the algorithms you can use and with a KD tree are going to be fairly fast as well. So to give you an idea of what it looks like with and without photon mapping, I have a small array of slides here. So this is all diffuse surfaces, so diffuse horse, diffuse wall, diffuse floor. And there's an area light up here that you can't see. So this is what you get. Kind of looks boring and plasticky. Definitely looks fake. Now what I can do is in the photon mapping, I can enable the global illumination or indirect light, the radiosity elements. The image gets brighter, as you can see, and that's because now we have light indirectly lighting other surfaces. The other thing to observe is that some of the colors of this blue wall have bled into the surface of the horse. There is a bit of red in the tail, but it's not very noticeable. And we got that through photon mapping. Now, photon mapping is going to help us with our reflection. So here is a reflected mirror horse statue, and it is, well, it's pretty boring to be honest. And we know that it should reflect some light onto the floor. Without our photon mapping, none of it. With our photon mapping, you can actually see the quality of the reflections is improved, but not only that, the light that is being reflected off of this horse statue is reflecting onto the ground and indirectly illuminating some of the other areas. We can also see that there's some caustic effects going on down and around the back of the horse, simply and around the base, where we have, rays of light that are focusing to create a brighter surface. The next one we have to look at is our transparent horse. So this is what you get if you render a horse without any kind of global illumination whatsoever. It mostly looks real, except the base looks solid black, and that's kind of strange because I know that the base is supposed to be glass because this is I set the material for the object. It should all be glass, but it doesn't look it. So this is actually with global illumination turned off. And here's it with it turned on. Now you can actually see through the glass floor base of the statue. And then we have subsurface scattering again. So you can see here that through subsurface scattering, we can actually see a little bit through the horse, and so we can, give it some spooky effects. So just to show you these again so you can see the difference, you've got your diffuse, no reflectance, everything is turned off. This is what happens when you turn on the global illumination for radiosity. We end up with a brighter image because now we have surfaces lighting other surfaces indirectly, but also we can see there's a blue tint to the horse and a bit of a red tint in some places if you look closely, and that is reflectance coming off of the walls. So, no global illumination, global illumination. The next one again, let's just look at this again, compare the two. You don't see a big change in the reflectance on the horse itself, but you do see it in the base where we are now reflecting light back into the scene in the caustic effects. So none, some. Slight differences. It really helps to put them side by side or to flip back and forth between them so that you can actually see the difference in lighting. And then here we have the one where you have a transparent object. Again, no caustics, no global illumination, and that's when you turn it on. Off, on. Obviously, when we have it on, we get a much more realistic effect, and we're much happier with that. Now, we're going to talk about performance of these algorithms in a little bit, but just to give you a heads up, like how long does this actually take? This image all the way back here took 27 or 29 hours to render. So beware that this is not fast by any stretch. All right. So we're pretty happy now, right? We've got the indirect illumination. We've got caustic effects. We've got nice diffuse reflectance. Can we render everything now? No, not quite. So I want to talk about another kind of rendering known as spectral rendering. And this is kind of a bit of a tangent to what we've been talking about. It's a different variation. That's a better word. It's a variation. So the idea is that when we're doing ray tracing, path tracing, photon mapping, we consider ourselves to be tracing a light of a particular color, usually white or off-white. It has a red, a green, and a blue component, and we don't consider the individual wavelengths. We just take the color of the light and we multiply it by some factor to give us its contribution. We've made the assumption that the contributions are equal for every possible wavelength. We've made the assumption that the index of refraction is the same for every wavelength. But that's not true. Let me show you. Because some things we still can't render. Even with all of those methods we just showed you, there's some things we still can't do. I can't do dispersion. So this is literally where you have white light coming in, and I know it's yellow in the picture, but it's white in reality. And it goes into a triangular prism, and the triangular prism ends up spitting out a rainbow, because white light, of course, is made of all the colors. We can't do this so far. We do not have the technique so far to cause this image to be rendered. And there's other things that we can't do as well. We cannot do iridescence, pearlescence. We cannot do diffractions. We are very limited in the kinds of surfaces still that we can simulate. But we can actually do these things using something known as spectral rendering. The idea behind spectral rendering is it's the same algorithms we were using before, except instead of doing just here's the color of the light and here's the intensity and go multiply it, we have to now render using light by wavelengths. So color, we'll use colors in terms of their wavelengths. The light, we'll now have to send more rays, and each ray will have a different wavelength. And so we're going to do light emittance is described by the wavelength. We're also going to now need more information for our surface materials because we need to know their wavelength properties. We need to know their spectral reflectance curves because some objects will reflect more of one color than another color, or they might reflect one color in one direction, like red light will get reflected this way and blue light might get reflected that way. So we need the spectral reflectance curves. Now this is obviously very expensive. The algorithm is simple because it's just taking what we did before, except now we're going to repeat it, and instead of using the materials and light colors that we had before, now we're just going to do things with spectral computations. But we need to now do many rays because now we are going to need to send rays of different wavelengths. And then we're going to have to combine, for all of those rays we send through the pixel, we're going to have to combine their results into a final spectral color and then convert the spectral color back to RGB. And I will also say that when you convert the spectral color to RGB, there is a potential to lose some of the accuracy because you can only represent a subset of colors with the RGB system. And so now we should be able to render some more interesting objects. For example, we tried to render diamonds before and it didn't work out. Maybe we should try again. So one of the interesting things about diamond is that it has a very high index of refraction. Actually not the highest index of refraction, so there's actually a stone whose index of refraction is actually higher. It's moissanite. I'm not sure if I'm saying that right. It's actually higher. Yeah, higher. And it's that high index of refraction along with the cut, the faceting of the stone, which gives that characteristic sparkle when you think of a cut gemstone. And it's actually really hard to capture that in a still image. This is a really boring photo, but one of the things that we expect when we see a diamond is that there's going to be a lot of bright reflected whites, but there's also going to be some rainbow colors being reflected back to us as well. That sparkle and that rainbow is actually arising from dispersion, the separation of light, because the index of refraction is actually dependent on the wavelength. So this is what we had before. So this is our cut diamond model, and I'm using no caustics and no dispersion, so no spectral rendering. It's boring. It doesn't look like anything. It looks like a gray rock. Yeah, I don't like it. If I add caustics to that, I do get some sparkle now. And I also see I get some sparkle on the ground below it, which is caustics. And I expect that because I've turned caustics on. But still no dispersion, so no rainbows. Looks a little better. So how do we do this dispersion part? How do we get the rainbow thing? Well, there's actually a lot of different ways you can do it. You can use spectral rendering, and we will in a minute. But before we try spectral rendering, are there any other ways that we could get those rainbow reflectance? Actually, yeah, there is. So one of the strategies we can use is to use an environment light that's a rainbow. And, I mean, you really have to make sure if you're going to use this strategy that that light is only applicable to the diamond itself. You do not want it to be applied to anything else. Otherwise, your whole scene will be reflecting that rainbow light. You can do that in a lot of applications. You can say this light only applies to this object. And if you use a rainbow environment light, actually you will get some rainbows reflected. We'll show you. And there's other things that you can use, like transparent textures that actually have that rainbow texture built in. But we're not going to do that one. We're going to do the rainbow environment light. So this is no caustics, no spectral rendering, but I used a rainbow environment light to produce the rainbow effect. Okay, so I got some plainer rainbow faces now. That's kind of cool. And if I turn caustics on now, not only do I get the bright sparkles and the internal light coming out, and I get the caustic effects on the ground, but I also have some rainbow effects. And they even kind of show up on the ground. Okay, that's cool, right? It's pretty cool. Going back to this, you know, it's believable. Now, the truth is, when we're looking at this boring photo of the diamond, this diamond here actually has a lot more facets than the one I'm using. So that can actually have an impact on how we are seeing the stone. So, environmental light, that's a rainbow, but no caustics. Environment light, that's a rainbow, and we added caustics. So we're getting some of the apparent dispersion. So now let's actually turn on spectral rendering, or at least a simulation of spectral rendering, and that's what we get. That's pretty cool, actually. It's got a lot of internal glowy features. Now, I have turned that dispersion up really high because I wanted a lot of rainbow. So this is caustics and dispersion. And if you look at the caustic effects on the ground, you'll actually see that the rainbows are projecting onto the ground, which is pretty cool. So this feels very brilliant. And what's cool is I can now combine this too, if I really wanted, with that rainbow environment light. And now I get that. And it's a little bit darker because the environment light is now not white, now it is a rainbow. But you can see it actually enhances the rainbow up in this area here. So we can now actually, with spectral rendering, caustics, and environment lights, we can now produce something that looks roughly like a diamond. But do keep in mind that it is actually very difficult to photograph a diamond. Now, what about some of these other nifty effects like iridescence and pearlescence? So iridescent objects, and I do not have any, are things where depending on the angle that you're looking at it, it looks like it's a different color. So there's some car paints out there where on one angle they're purple and on the other angle they're green. You might have seen them. There's certain beetles. There's these green beetles that are iridescent, and they might be pink and green depending on the angle you look at them. If you see oil spilled into water out on the ground, you'll see rainbows. So it's got some iridescence effects. And there's also this concept of pearlescence, which is very similar to iridescence in that we are seeing rainbows and the appearance of the material is different based on our viewing angle. The big difference between iridescence and pearlescence is pearlescence, in addition to reflecting some rainbows, also reflects a lot of white light. So it doesn't have as brilliant of a rainbow reflection. These appearances are properties of the material, the surface. A lot of it is because they have this microscopic texture that is bending and separating light, similar to diffraction grating, and it's actually separating the light, which is pretty cool. But you can't usually see that. Sometimes it's just subsurface that it's happening, and sometimes it's right on the surface. So, that's things like bubbles, which is really cool. That's an iridescent example. And pearls and things like that. And again, this doesn't photograph well for a lot of stuff. So how do we do this? These are really difficult to simulate accurately. And in fact, none of the techniques that we've shown you so far will do it straight out of the box. Yes, spectral rendering is going to be needed, but you're going to need a bit more to give you that iridescence and pearlescent effect. You could fake it. We showed you how to fake the rainbow effect in the diamond using things like environment lighting. You can also use spectral rendering combined with subsurface scattering. You can actually create layers of subsurface scattering. There's also textures, carefully constructed lighting. There's lots of different things that you can do to actually simulate these particular appearances. It's not to say it's going to give you a perfect result, but you can get some pretty convincing results by doing this. Now, I keep saying this, but this indirect lighting, be it radiosity, be it path tracing or photon mapping, and spectral rendering, and photorealistic rendering, it is all really, really slow. Because in order to produce really high quality results, we actually need to send a lot of rays, a significant number of rays, hundreds of rays per pixel, or tens of millions of photons in addition to that. So it's going to be very slow to do these, but you end up getting a much more realistic result. Now, over the years, we found better and better ways of doing this by finding little cheats that we can do to simplify things and get a reasonably accurate result. Things like limiting computations to specific lights or objects in the scene, which is something I'll show you in a minute. Something that a lot of tools do is they separate the radiosity from the caustic effects, so you can have either one or the other, or you can turn on both to try to limit what's going on. And a lot of the time too, we're just using textures because we get a good result and it's really cheap. So global illumination is the desired thing for photoreal rendering, but it's really expensive. So if you have some way that you can simulate it without the cost, that's often the preferred strategy to go. All right, so here's a few review questions. You're welcome to take a look at those. Before we end for today, there's one more thing I'd like to do. I'd just like to show you how to enable some of these features in Houdini for anyone who's interested. So here is actually the scene that I rendered. It has a, this was Caustics plus the environment light plus spectral dispersion. And this actually didn't take that long to render. It took an hour and 18 minutes. And I think that's actually because I didn't use the ray tracer for it. I used a different technique. So what I want to show you is we're going to go into the scene view. So you can actually see my environment light. It's a repeating rainbow. So it's going to be everywhere. You're going to want to make sure this only lights the diamond. And that's going to be really dependent on your tool. Now, how we enable caustics and global illumination in Houdini is with different light sources. So they have them separated. So there's GI light for global illumination light, and that is going to be the indirect for diffuse surfaces. So if you add this, it's not an object you can physically move around in the scene, it's just enabling it. And it has lots of things like you can increase and decrease the intensity, and then you can also select the number of photons you want to send. So in this case, this one only has 100,000 photons. And then there's a caustic light as well. So this is actually the caustic light. And if you want to get a really accurate version of this, and actually for photon mapping, which is not trying, it's trying to estimate a solution to the integral, but it's not accurate. The more photons you use, the more accurate of a solution you will get. I tend to use 10 million photons. I like the result. The more photons you use, the smoother and the cleaner and the more realistic the result is going to be. Fewer the photons you use, the grainier and the noisier it will be. So I like to use 10 million. You can use whatever you like. So the caustic and the GI light have roughly the same properties. And then for the actual diamond itself, I know it's labeled glass. It's not glass. I just use this as the base material to which I manipulated. So I've set the index of refraction to 2.417, which is the index of refraction for diamond. And I've set the reflectivity to 1. And then down in transparency, I've set dispersion to 2.5 because I wanted a lot of rainbows. And that is actually going to give us that really intense rainbow dispersion. And when we combine this all together, we end up getting that image there. This didn't take that long because if I actually look at which render tool I used, oh, I did use ray tracing. Okay. But I didn't use that many photons, so it's not that accurate. Now, it's important in your renderer to make sure when you're different renderers are going to enable these features in different ways. So in Houdini, you actually have to add the light. And then you can also do things like physically based rendering and so on. So make sure you have the correct rendering engine chosen for this. And if you want the caustic effects without the cost of the caustics, there's also a caustic simulator where it tries to fake it for you without actually doing all the work. So that's also another thing that I recommend looking at. All right, so that's a very quick overview of the 3 different things I use to compute this scene here. I'm going to leave that here for today. In our next lecture, we're actually going to move away from photoreal rendering with ray tracing. We focused on the actual simulation of the light rays so far. So where are these light rays going? How are they interacting with each of the surfaces? Ray tracing and path tracing and photon mapping, they give you the most photorealistic results. They're also really expensive. A lot of rendering these days is actually done in a different way, using things like OpenGL and just rendering triangles and using shaders. So what we're actually going to look at in lecture 6 is how to do some of these things with shaders and the rendering pipeline, as opposed to actually simulating light to solve the rendering equation. So that's lecture 6. Lecture 7 will be a tie-off for the photoreal component of this course. So we'll look at a few recent developments that have really improved the speed to get caustic effects using more Monte Carlo algorithms. And we'll look at things like stereo cameras and different things like anti-aliasing and so on and so forth. And then after lecture 7, we will move on to the second half of the course, where we're going to talk about non-photorealistic rendering. So right now we focused on how do I make this artificial diamond actually look like a diamond? And in the last half of this course, so lecture 8 and beyond, we're going to be like, how do I make it look like a pen and ink sketching of a diamond? So that will be lots of fun. All right, we will talk to you next week then.